So today we'll be doing another EE140 old midterm problem from spring 2015. It was the midterm 1, and the problem is as follows. A total charge Q is deposited on a conducting sphere with radius A, which is shielded by a metal shell of inner radius B and outer radius C, as shown. The outer shell is grounded outside, and it's asking to plot the E field as a function of R, and clearly explain your answer. It's also asking, what is the surface charge density at R is equal to A, at R is equal to B, and at R is equal to C? So, I drew the problem just to make it a little bit easier. I simply labeled what was given to us, so we know that when it's this first sphere is just a conductor on the inside, and it's air in between, and then the outermost shell is just a metal shell, and it's also just a sphere. So to plot all the E fields, we just have to find the electric field at each radius or each part of this sphere. So let's first look at the first part, when R is less than A. That means we're looking at the first shell. And it's important to understand that this shell is a conductor. So all that means is the electric field will just be 0 when R is less than A. But it's important to remember the problem, and we have to understand that a charge Q is deposited on a conducting sphere. So although we know that the E field is 0 inside, all the charges will be on the surface of the first shell, which we can use later. So the second part, which is going to be when the radius is in between A and B. So because it is air, we know that there has to be some sort of electric field in there. So, using Gauss Law, which is the closed integral of E dot dA, which is simply just flux, over the Q inside divided by epsilon naught. So, to make this easier for ourselves, let's just choose a Gaussian surface, and the most obvious one will just be a sphere. So that means the area for this Gaussian surface would just be a sphere, or the surface area of a sphere. So our dA will just be 4 pi r squared. So plugging it into our equation, we can get rid of the integral. So E times 4 pi r squared is simply equal to the charge over epsilon naught. So that means, sorry, forgot the vector right here. So all that means is E is simply equal to Q over 4 pi r squared times epsilon naught in the r direction, r hat direction. So the third part will just be when R is greater than B. So when R is equal to B, which means it will be inside this metal shell or outside the whole sphere, we can just say the electric field will just be 0 because it is a metal shell. And also the outside is grounded. So the electric field is simply 0. So we now have the electric field for each portion of the given sphere. Now we can plot this. So to plot it, you simply draw the plot. This E and R, and we have three sections: A, B, and C. So, looking at the equations we calculated, when R is less than A, it's going to be 0. So, that means when R is less than A, it will be 0. But from A to B, we have some sort of electric field, which will just be Q over 4 pi R squared times epsilon naught. So we simply just have to plug in A into our equation, and we will get, so at A, the electric field will simply be Q over 4 pi A squared epsilon naught. I simply plugged it into this equation. And at B, we can do the same. So, you should remember that 1 over R squared simply looks something, the graph looks something like this, since we're plotting it with respect to the radius. So, that means at A, let's just start A right here. You can call this point Q over 4 pi A squared epsilon naught. And it goes down to B, which at that point we know it will be this. Q over 4 pi B squared epsilon naught. Then we also know that when R is greater than B, it will simply just be 0. And that is the plot for the E field. So now moving on to the third question, which is just asking for the surface charge density at R is equal to A, R equals to B, and R is equal to C. I will just do it on this piece of paper. So the equation, if you don't remember, is simply the surface charge density is just equal to Q over A. The Q is just the charge and A is the surface area. So doing it for the first part, I use a different pen color this time. So when R is equal to A, it will be equal to Q over A. And the question comes, what is the charge? Well, as I said earlier, looking at the sphere, we know that a Q is deposited onto this conducting sphere. And because it is a conductor, we can say that all the charge will simply just go on the surface of this sphere. So at R is equal to A on the surface, the charge will simply be Q, which is what was deposited in the beginning of the problem. So it will just be Q over the surface area, which will just simply 4 pi A squared. And this will be the surface charge when r is equal to a. At r is equal to b, we use the same formula again, q over a. But this time, what would our charge be? Well, if you think about this, since we know that at this surface it is a charge of q, that means at this surface right here, since opposites attract, it will be negative q. So you can think about it as the positives charging the inner sphere, which attracts the negative charges from this point to here. So it will be negative q over 4 pi b squared, which will be our second surface charge. And the same thinking can be said for our last one, r is equal to c. Well, for this case, we know that because it is grounded, the surface charge here will just be simply 0. But let's just say we have another scenario where it is not grounded. Then the charges will just be positive. Because if this was positively charged on the surface, and it will make the induced charge negative on this second surface, which then will attract the positive charges on this most outer surface. But because it's grounded, we can simply say that the surface charge density is simply 0. And that will be it for this problem.